So this is the primary interview process. The purpose of this presentation is to make sure all the sub-teams are moving along in their research and make sure that there's no holes within the model-based design timeline. We're with the structures team, with the team lead being Diego Salvatierra. Diego?
Yes, team lead for structures team. My design team is Chase Webb and Samuel Shasha.
Chase Webb here.
Sam Schaefer.
Okay. All right. Ready? All right, so the mission statement. So our goal as structures team is to provide a stable housing unit for the internal payload of the CubeSat. We hope to achieve this by using SolidWorks to model the external frame as well as the internal fasteners. Once completed, we will conduct both structural as well as thermal analysis to ensure the proper standards are met. Based on the results of the analysis, we will optimize the CAD model and move towards a working physical model. After completing the test in the physical model, we hope to present a stable satellite which will be ready for launch. All right, so for materials and infos, it took us a little bit only because we were looking for some materials that had the least outgassing properties. At first, I did think about using carbon fiber, or it was carbon resonant because it had low outgassing properties, but we definitely decided to go with 7075 because it's cheaper, it's more accessible, and it's easier to work with. Fasteners will use 316 stainless steel anodized. Also, the frame has to be anodized as well. So both of these, both the fasteners and the actual structure have to be anodized. We'll talk more about that later. Fastener types will be using standoff screws on the internal side of the structure. Again, I'll show you that in the 3D models. And those will separate the PCB boards from each other, depending on how much space each subsystem needs. For example, if the experiment needs 5 millimeters, 6 millimeters, we will adjust the standoff screws accordingly. To put it all together, we have countersunk screws, 3 millimeter diameter inside and 3 millimeter diameter on the outside. And for epoxy, we did a little research and we found that Epotech 4110LV is a epoxy that we can use on the fasteners that is also approved by NASA. It's been used on other CubeSats as well. We're also looking at F253, but we're still a little iffy on that one, only because this one has a lot of research on this particular epoxy brand. All right, so the walls of our CubeSat are going to be PCB boards based on F4 boards, 1 to 2 millimeter thickness. Unfortunately, solid boards at the moment, we're not able to get the actual PCB board material, so we instead, Sam was able to accurately represent the properties of 4 boards for our simulations and all that.
Right, so there's specific property tables that have been researched for the specific types of PCB boards. So we chose the most common one for this application, which would be like an F4 board. And we basically took those properties and we put it into a custom material so that we can get as close of a resemblance during our testing and things like that.
So I'm going to be speaking on the design, the draft, and materials concerning the design and model for our CubeSat frame. What we have here is version 4.1 of our drafts for our CubeSat satellite. We've actually right now progressed marginally forward to 4.3, where we have standoff shelving on the internal structure of the arms for the spacing for technologies and experiments. Irrelevant to the design, so we decided for drafting purposes to stick with the 4.1 draft for this area. Mass is only varied by about 5 grams without the standoff attachments to the arms. So as of right now, you have on the left side of your screen the full assembly, which is set up by a trimetric perspective, as well as the front, bottom, and top views. Moving to the right here, we have the main assembly frame components. PCB board being a vertical component and a horizontal component, where one length is longer than the other one. Then you have the vertical assembly arm, and below that are the top and bottom panel, which are exact copies of each other, just mirror each other itself on the wide plane. Now, the vertical assembly arm is actually faceted through the perpendicular plane of the top bottom panel. not just through countersunk screws that go into the frame design and material by 9.5 millimeters, but also is also socketed in the corner of each corner of the top and bottom panel on the top and bottom of the arm. So there also is a preventive measure for any sort of rotation because it's socketed into a corner at each of the bottom and top section of the arm. So not only do we have the fasteners holding them in place with extra torque to prevent rotation in the Z direction, but we also have fasteners on the plane and design into the model that also will prevent it. Basically, it's like a Lego structure built together, and the Lego prevents any rotation. Moving forward to the next slide. We went with the crossbar design for top and bottom panels because the strongest structure for most designs over the history of human existence have been a triangle, 60-60 triangle for even and fair distribution of load and vibrational structures. The four sections for equal load distribution and equal vibration dampening properties. For example, as sinusoidal vibrations travel through the structure, they will dissipate across the design due to the 5 millimeter radius circle in the center, which also, by the way, is 1.5 millimeters thick, which this will disrupt the traveling medium as sinusoidal waves travel from the X-plane and across the X-plane through our structure during launch, during deployment. And not shown here, but as will be illustrated, the internal outcrops from the arms parallel to the y-axis here will provide the spacing for experiments and technologies. And we'll have literally shelving, in lack of a better word, inside to hold up and provide dampening for technologies and for the experiments. Next slide, please. Now, after some market research and industry analysis, the production of the CubeSat will and most likely have to be done with CNC milling process, which will include the 6 parts, 4 arms, and 2 top and bottom panels, all made from aluminum 775 T651 materials, which will be anodized at finish, and we'll have the deployer arms, which are the outer ends of the top and bottom panel brushed. The metal will be brushed so that they will be compatible with the deployer system in the ISS. The machining will probably be the most expensive part of the process, but we do actually, after going to different manufacturers across the European Union and the United States, we do meet nominal requirements and minimal tolerances for manufacturing. In these CNC companies, they do require like minimum thickness, nominal tolerances, and minimum drilling spaces. And as of right now, I haven't encountered any problems with our current dimensioning and their minimal requirements. So as of that, we're compliant with manufacturing standards so far and knowledgeable of their requirements. Next slide, please. Actually, I'm quite sorry. One slide, please. Did not touch on this, but the rough estimate for our CubeSat cost, including materials, production, CNC milling, anodizing, and brushing, will be between $2,000 and $6,000 expected. The final approximation would probably want to be maintaining a high quality of materials in production. I'm guessing, in my professional opinion, around nearly $5,000 for all of the components assembled, anodized, and the deployer arms brushed properly. Next slide, please. Now, the material data, you have the 6 components for the frame, and then you have 2 PCB boards, that's the vertical design, and then you have the 2 horizontal PCB boards as well. And to total these all together, we have roughly 235 grams as the total mass, including PCB boards. Without the PCB boards, just the metal, the aluminum 775 T651 will be a total of I think it was 180 grams roughly, which compared to other schools and other CubeSat launches that match 1U, we're within the average of those masses, but we're towards the upper end. So as we go through other version drafts of our CubeSat, we will have changes made to the thickness and to other dimensions, which in the end will probably keep it around the same, if not drop it a little bit. On the end of this table here is the estimated cost of the materials itself. After doing analysis of the average cost per gram from Alibaba and other sources of raw materials on the internet, 35 grams, 35 cents per gram is the rough cost of the average price for aluminum, 7.75 per gram. And our materials cost for any manufacturer should be less than $50. So, like, just to prove my point, machining will be the most expensive part of our production, and that's why it's very vital and important to be someone who's going to go out to the market and shop smartly and understand that we have a competitive edge if we get different price points throughout the market and compare openly and transparently with our possible manufacturers so that they can compete for us. Okay, and next slide. Sam.
Yep. All right. So one of the things that we're looking at to protect our Q satellite is shielding. So we're looking at using RF plasma sprays or wraps, in particular at the atomic level Z, to shield. So one of the ways that NASA does their satellites is through the Langley Research Center. They basically have facilities in place where they will coat the satellite with a spray, and it will help protect the electronics and the internal payload. Now, the way that the spray works is, from a cost perspective, the cost becomes more beneficial on a larger scale than on a smaller scale when using sprays. So another option that we looked at is wrapping it in specific materials to see if we can also reduce the lifetime that way. Now, for the surface area, we estimate the cost to be from under $1 per spray to more than $50 if we were to just, purchase the spray ourselves. In small volumes, like I said, the robotically sprayed coating has a premium, so it's easier for a robot to do it, but if it's a smaller volume, the price might be more than what it needs to be for us. Next slide, please. Okay, so the launch simulations. So there's 3 simulations as of right now that have been done. So we did the initial launch, and then we did the heat flux. So right now what you're looking at is 2 millimeter velocity. You have the stress is going to be on the right, and then the displacement is going to be on the left. So let me pull up these values right here. Okay. So the von Mises stress is at minimum is at 32.46 Newton per meter square, and then maximum it's going to be 6.26 10 to the 6th Newton meter squared. Now, when doing these simulations, so the pictures you see right now is for the first step. There's 100 steps in this simulation, and we're going to be running them again to include more steps and include a longer time duration so that we can see per network requirements for the 3-minute mark, okay, what really is it going to be doing in those 3 minutes? So in terms of any issues and things like that we may have run into when doing the simulations, there was a slight flex on the positive and negative Z faces of the CubeSat, which was to be expected, as right now there's nothing that's really preventing that from happening, as there's nothing internal. Like they were mentioning, the shelving and things like that would also provide us with an internal skeleton to the model. So one of the ways that we're looking at fixing that is to add another crossbar, like you see on the top of the Y face there. by adding that on the PCB faces and then fixing it with a fifth screw hole. By doing that, then we can eliminate that flexure, and through the optimization process, we should be able to do it with little to no weight change on the overall model. If you want to go to the next slide, it's essentially about the same thing. The only difference is the testing condition is with the 2 meters per second squared acceleration. The acceleration did flex a little bit more at the initial than the velocity, which is to be expected as it's more of an impulse. But what happened with these models is that over time, and like I said, this is within like a matter of, you know, a couple seconds, right? The initial force being applied will cause us a slight deformation and a little bit of a wiggle, but then it will even out and there won't be any deformation. It will basically be a static and rigid body. So what we're going to be accounting for is that initial force, so that it's static and rigid throughout the entire launch process to ensure the safety of the payload. The specific values that we're using here are per the NanoRacks providers documents for the launching conditions from the P-pod deployer. If you go to the next slide. So we have the heat flux simulation. This is using the solar flux. This value has been researched, and they found it to be about 1,353 watts per meter squared. So as of right now, we are still processing this particular data, and we expect this particular data to shift once we apply the coating for the shielding. That will help with the thermal flux and things like that we'll encounter. For Diego, do you want to do the next steps?
Diego, you're muted.
Thank you for that. Yeah, so for feasibility, we're setting around $100 for hardware. This includes fasteners, epoxy. The reason why we put so much is just because we might have some models that we make, and we're obviously going to have to use some fasteners for that. So we're not expecting to go anywhere over this at all. In fact, we're going to be way underneath, kind of like what we were looking at, $80, probably around the $80 mark. As far as the structure price for CNC, we are waiting for quote from Proto Labs. We are in talks with them to complete that process. Based on our research, we feel confident that with proper shielding, payload will be protected from the environment of space. We're doing a little more research on that, as you can see in this third slide. As for the structure itself, we're currently undergoing the optimization process to decrease any deformities due to stress it will encounter, as well as decrease the overall mass of the structure. From the test so far, the stresses are manageable, and we believe that we can produce a structurally stable satellite. Real quick, I want to show you something. It's the other way.
Right. So, yeah.
So for this, for our next steps, as you can see here, we have the 8 holes for our standoff screws. Really, what our next steps are is we have 3 goals. We have maximize space, minimize weight, and maximize strength. So one way we can do that, obviously we talked about the X bar design right here on the top and bottom, the Z plus and Z minus faces. That's good for strengthening, obviously, according to our simulations. And then the next thing we can do to maximize space is to fine tune these arms. If I can just show you real quick, I'll take away the PCB boards. Oh, take away the top one as well. So let me do this. Oh, sorry about that. Okay, so here you see that there is some space that we could maximize some space with. We could move this slightly over to the right and this one slightly over to the left. We would have to run simulations on that, but really at this point, it's fine tuning. Only because the inside of the structure is very simple. It's the easiest part of our design because we're going to be using stand-up screws. That's literally all there's going to be inside for the skeleton of the structure. But really, we're focusing on the outside part, which is our hardest part, most challenging part. All the internal design will be a lot easier as long as we maximize again strength, weight, or minimize weight and maximize space. Go back to the presentation real quick. Cool. So we're currently finishing TRL3, the simulation phase of the design process. On completion of this phase, we will move towards the 3D printing model to conduct visual test on. Once the printed model has been tested, meets the requirements, we will create a prototype model using the actual flight materials so that we can confirm launch readiness. This is why we're putting aside the extra money for the hardware, just so we have to run with this thing. During the time from the kernel to flight, our team will be focused on stress simulations, finding models that shield the model from environments, and protect the payload from those elements. Basically, what I said, our next, visually, I try to show you what we're going to do. Move the arms to the right a little bit, lower the weight, and do the simulations as we do so, as we move on, so we can make sure that we're doing the right adjustments. All right, Sam, you want to go this one?
All right, so further testing that we're going to be conducting on this, like I said, the current tests that have been done have been just the initial conditions for the nanoracks, the P-pod. So what this is showing is per NASA. This is basically a specific test that they require in order for this to be deemed flight ready. So the right-hand column that you see here, this is the qualification. So there are three columns where basically there's a proto-flight, there's a testing, and then there's the qualification. So what we're trying to shoot for, obviously, is the qualification. So the testing that we're designing for is for those optimum standards so that it's ready to go when it needs in the first trip. So what are some of those tests? We have the random vibration, sinusoidal vibration, we have a shock test, thermal vacuum cycle, there's a bake out, and then there's the strength analysis and the structural test. So the random vibration, or the vibration tests will likely be done in SolidWorks. As for the shock test, looking currently into using ANSYS to do that, and we hope to have these simulations done within the next week and a half to two. Yep, that's it.
That's it.
Okay.
All right, guys. Any questions about our presentation? Any questions about the structure, our next steps?
Yep. So I wanted to ask a question for Chase. If you can go back to the diagram with the measurement specifications, the drafting model. Thank you. You're mentioning that you're doing countersunk screws. Have you found any specification for the countersunk drafting angle within the aluminum? You're muted. Go ahead.
The angle you're referring to is the pitch between the inner and outer diameter of the countersunk screw. Yeah, we already have 45-degree pitch. Most countersunk screws are 45 just because they'll have less of an effect on any metal and breaking or nibbling away of the valuable metal. So 45-degree pitch is the standard. Even if you go to Home Depot, look at countersunk screws, it's usually about between 40 and 47 degrees.
Okay. That was, I didn't see, I see you wrote it in the bottom left corner. Okay.
Yeah, it's there. I include all that relevant information.
Perfect. The next question I wanted to ask, this could be anyone who wants to answer this. What is the reasoning between building your own structure rather than buying one that has flight heritage? I mean, if it's already been flight proven and tested on numerous CubeSats, and we as a team simply just adapt to that frame that's there, why did you decide that the best method is going to be to build and test your own?
May I?
Yeah.
Go ahead, Jess.
Coming from the person who did majority of collaboration and work for the design currently on hand, just because my forte tends to be in modeling, I'm not a simulations person. I'm not as knowledgeable on that as well. And my team lead, Diego, is amazing when it comes to organization and oversight. For me, the reason that I think it's integral for us as a team, structures team, and as the AXA CubeSat for FAU to design our own CubeSat for launch is rather than host our experiments on some already pre-done structure that has been flown and test proven, because you're taking away the process of learning and also taking away the opportunity for a person to develop a new design or a new model that is either relevant or supersedes any other previous model design that could be out there. You take away the opportunity for innovation and for other collaboration, because if I come up with something that maybe someone at Cornell or Berkeley or University of San Diego didn't come up with when they were designing theirs, I came up with something that they may not have thought of. And before you know it, that idea gets spread and hybridized and incorporated into new relevant designs. And you find out that multiple ideas together create a more efficient design than any individual one separately.
Okay, so Sam, I turn to you. Have you been able to find any test results of other flight heritage CubeSat structures to compare your teams to make sure that you guys are up to par and your satellite's going to work? Or is at least on the market to be comparable to other structures that have already flown in the past? Because I mean, it's good to have, building the team and understanding the ingenuity piece of it, but we still want it to work. So what have you done to make sure that the satellite is up to par?
Right. So currently we've just recently started the simulation. So I cannot currently give strong feedback that this has been compared to other satellites. But within the next week, we will do the research to compare to heritage satellites to ensure that our values are up to par with them, if not better.
Okay.
Also to add to that, another advantage of having our own satellite or our own structure, building our own structure, is that gives us the flexibility to work around the experiment. We can be experiment specific for everything. Sometimes for the structures, they might come out, for example, structures on the market. They're great, but the thing is, customization can cost a lot of money. Usually they advertise the standard model, kind of like a standardized model for all experiments, but in reality, our experiment and other experiments, they all require different capabilities from the structure. So maybe different points of visibility for the sensors. That's another reason why we decided to go with our own design moving forward.
Okay. Another question I wanted to ask is, have you gotten in contact with either the communications team or the power supply team and understand how you're going to mount the antenna and the solar panels onto the satellite? Because I didn't see that in any of the models.
They will be fixed. Yeah.
How are you fixing them onto the satellite structure?
You want to talk about it?
Yeah. So the solar panels will be fixed onto. We talked with the power supply team last time, and we confirmed that we're going to be using fixed. So the reason why we're using PCB board on the outside of the satellite is not only for weight, but it's also because we've seen other satellites, for example, the MSP satellite, the Baltimore Space Program. We're able to attach their fixed solar panels onto the PCB board inside of them on. And so that was very efficient because it's both lightweight and it also uses the max amount of space you have around the satellite. So we're mounting them on by basically placing them on, you can say, basically very thin films onto the PCB boards that we have around the satellite.
Okay, and what about the antenna and the antenna deployments procedure?
Okay, so antenna deployment, we do have to get in contact with them, that is, we do have to make some space on the top of the satellite because usually the antenna comes on positive Z-axis. flicked out on the top. We just have to make some space for that on the PCB board. Maybe it's flat. We do have to get more content with the communications team specifically for that.
Okay. Now, something that's really big that I haven't seen at all in the entire presentation is your own PPOD deployer. When do you guys plan on building that and doing testing with your specific model on a PPOD deployer? Because each team has to make their own deployer that gets put on the ISS launcher. So your deployer is inserted in it, and then your satellite comes out. So have you guys started the design of that or researched into the specifications for that?
We actually were aware that we had to make our own PPOD.
Yeah.
Yeah. You do. There's a whole design specification list inside of the CubeSat 101 manual.
Okay, yeah, we were under the assumption that we have to design the CubeSat around the PPOD that they provide us, and that's why there's so many measurement specifications. That was our idea.
Okay, so I would say I could be misspeaking if you've read some information that's different than what I've read. So I would say I sent in the Slack group chat a technical document with all of the design specifications for the PPOD. I would say either way, whether our PPOD is not put on the deployer or if it's the deployer that's on the satellite embedded in the system on the ISS, that you build your own and test it, given the specifications that they give, because they're so specific to the extent that you can actually build your own deployer with that information they provide. It would probably be in your team's best interest to build it and start doing testing with that to make sure it actually works. And one thing I wanted to ask is, have you guys discussed about how you're going to do the finishing on the rails? I know that the rails need to have a specific level of, whether it be, I don't know if it's a brushed finish or if it's a kind of like a sandpapered finish. Do you guys have the?
It is included. It's a brush metal finish. And Jake, per our interview with Proto Labs and Jenna Simmons, they did express that, at least in their CNC milling process, that they can brush the metal on the P deployer arms. And I believe it was at no extra cost either. They also mentioned anodizing the aluminum 775 during the process as well when it was finished.
Okay, awesome. So you mentioned the RF spray. What does the RF stand for?
What?
Radio frequency plasma spray.
So is that going to inhibit any of the communications on the satellite? Do you know? Or for that matter, will the PCB boards be an inhibitor for the satellite to communicate?
So for that question as well, we're going to have to, again, like I said earlier, our communication with, or our talks with communications, you have to go up a little bit so we can answer this question.
I can answer the question in part. I've been reading up on the shielding. The RF plasma spray is supposed to cause the refractive elements of any sort of electromagnetic radiation from outer space to be deflected, while our radio signals are transmitted at a much shorter wavelength. They should be able to penetrate the shielding, but also we're emanating our communications from our antenna, which will be partially external threat from our satellite. So it shouldn't have any interference pattern towards it at all.
Okay.
Whether we use RF plasma spray or the atomic level wrap, either way, that's just for electromagnetic radiation mostly, which is a different wavelength.
Now, with most items that you're going to be spraying on, I'm assuming you're not going to want a lot of particles in the air. Are you requesting that we get a clean room to conduct the spraying because you said it would be cheaper?
No, we might not have to do it. There are companies out there that do this service. The bottom three bullets on this slide are from a company that does do spray. These are quotes, rough estimate quotes from their Q&A section on the website pertaining to cost. It's hard to find any rough costs on the internet regarding this industry. So I would go as to acquire these numbers as maybe at least a bare minimum for services to apply RF plasma spray or atomic level wrap to a satellite or extraorbital vehicle.
Okay, so basically what you're saying is you're not sure which one will be more cost effective right now.
As of right now, no, just because we don't even know the exact square footage of our final satellite by the amount of panels it would have or due to the cost of materials. And not until we have a finalized draft model and we can actually acquire the data per square footage, as well as in their website when it comes to applying the spray, they charge more for micro changes in geometry. So when you go from 1 millimeter thickness to 1.5 millimeter thickness, that changes the cost of spray, because then you go from automation, which is mostly done by robotics, you have to do it by hands. And that's where a professional will come in and start doing it there. So there's a lot of variables that go into having this done by a third-party company.
Okay.
And I'd want it to be done by a third-party company if we did.
Gotcha. Okay, so that concludes the questions that I had. I just want to bring reference to the CubeSat 101 document. This might be something to write down. Page 69 and page 79 are definitely some documents that your team is going to need to write. These are called the orbital debris assessment report inputs, which you'll be working with for the environment team to make sure that it meets the requirements for the orbital debris assessment, as well as the CubeSat acceptance checklist. These are going to be documents. There's also one more in here that I saw that you're going to need to fill out. Yeah, so page 70 has an example ODAR, and you're going to need to work with the environments team, because that's going to be something your team's going to need to output, and that's going to need to be in the proposal. So the sooner you can conduct your testing and provide those results, the better, as well as the acceptance checklist on page 79 to make sure that it passes the dimensional analysis, as well as the deployment switches, spring plungers, any protrusions, the standoffs, and an access port. I didn't see an access port on yours. It might just be because it's an early model, but just make sure that you guys find some way on the negative X and the positive X side of your satellite that you have an access port, so that the NASA team can access our equipment when we pass it over to them, and so that we can as well. That is a standard on page 79 that I didn't see. And it's not like, this is the primary interview, so we're just making sure we're identifying all those holes. So some documents there to start keeping nearby on a clipboard next to you as you continue in your secondary process, and make sure you're contacting the communications team for that antenna, the power supply for the solar panels, the environments team for this ODAR checklist, and just continue your testing with the experiments team, and make sure you're communicating to them on ideas that you guys might come up with for how to conduct testing in-house to save us some money. But you guys seem to be on the right track. I haven't seen any major holes in your subsystem so far, and just be ready for the next set of interviews in about I would say 3 or 4 weeks from now. But nice job, guys.
Sounds good.
And we'll talk later. See ya.